All right, guys, so this is the practice that you're going to be doing on your own here. And it is a little bit cumbersome. Whenever I did it, it took me about 5 pieces of paper. There's no way I could fit everything actually on this paper, so I highly suggest that you use notebook paper when you're going through these examples. There's your first one. You're going to be creating gene maps just like we did yesterday for each one of these from the last video. You guys know how to do all this. So I wanted to skip down to this part right here real quick. It says, for a series of experiments, a linkage group composed genes of W, X, Y, and Z was found to share the following gene combinations. Our combinations are expressed per 100 fertilized eggs, construct a gene map. And this gene map looks way different than the other ones that we've been doing. It's in a table format instead of very nicely labeling, oh, here's T and R at 21, here's T and S at 5. Instead, you kind of have to make this yourself. It's really easy. It doesn't have to be difficult at all. So W to W is 0 because W is the same gene. Okay, W to X would be 5. So if you wanted to write this down, you would just go W, X, 5. W, Y, 7. W, Z is at 8. Then we go down here, XW is at 5, which we already did. XX, XY, we don't have XY on here yet, is 2, and XZ is 3. Now you really need to watch to make sure that you're not duplicating here. WY is 7, which we already did. WX is, did we do that one yet? Yep. Or YX, sorry, is 2, which we already did. YZ we haven't done yet. All the Z's, you probably did most of those already. We got ZW is at 8, which is here. ZX is at 3, which is ZX. And ZY is 1. So this is going to be your gene recombination map that you'll be doing for the numbers. There is another one like that as well, a little bit farther down. Right there. Same basic idea. You can create a map that looks just like the one that I did above. Just label your A to B, A to C, A to D. Make sure that you're not duplicating anything. This one is one that you guys have already, you know how to do that one. It's the easy type, only doing 3 letters. What is the correct sequence of genes A, B, and C on a chromosome? You can draw a picture of a chromosome and label the genes accordingly. So what they're saying is to actually draw a chromosome, and then you're going to have bands because that's where your genes are located. And you would label those bands on that chromosome. So tell me where A, B, and C are. Again, another map, which you guys already know how to do. And another map. You don't really need to worry about the information up here so much, but it does say that it is a challenge question. And I'll be honest with you, this one is difficult. Make sure that everything makes sense as you are doing it. This one took me a few minutes to actually figure out because I had a couple things wrong. So really take your time. There are 3 genes on a single chromosome. Exhibit the following frequency, just making a regular map. Determine the order of genes on a chromosome. So again, you'll draw out a chromosome, throw your bands on there, and label them A, B, and C. This one, they didn't give you a table. Instead, they are giving you the percentages there. Test cross shows your combination frequencies A and B is 28%. Between A and C is 12. Can you determine the linear order of these genes? So do you know which comes first, A, B, or C? And explain if you can or if you can't. You know how to do that gene map. And this one, use the table. This one is even easier than the other ones are because I deleted pretty much everything out of there for you. You would just be creating a map like we have from the other tables. This is the one that I really wanted to do with you guys. It's the last question on there. And this is the one where you need to use a little bit of math. It's that formula that we had in those notes. So there is no gene map that you're going to be making on this particular example. So you're going to take your recombinant frequencies over all of the frequencies. You're going to divide those, and then you're going to multiply times 100. So space probe discovers a planet inhabited by creatures who reproduce with the same hereditary pattern seen in humans. 3 phenotypic characters are height, head appendages, and nose morphology, and snouts. They're turned up or down. Earth scientists are able to do some controlled breeding experiments on them using various heterozygotes. For a tall heterozygote with an antenna cross, the offspring are tall, antennae 46. Dwarf antennae 7. Dwarf no antennae 42. Tall no antennae 5. For a heterozygote cross with antennae and an upturned snout, the offspring were antennae upturned 47, antennae downturned snout 2, no antennae downturned snout 48, and no antenna upturned snout is a 3. Calculate the recombination frequencies for both traits. These will be 2 separate math problems. So whenever you're looking for recombination frequencies, remember those are the things that show up in the smaller amounts. So we have numbers here. Tall antennae is 46. Dwarf antennae is 7. Dwarf no antennae is 42. And tall no antennae is a 5. So those are our numbers for the first one. And if you're looking at that, you should be thinking, okay, my recombinant ones are going to be the 7 and the 5. So take 7 plus 5, and I'm going to divide that by 46 plus 7 plus 42 plus 5. So you would get your answer there, and then you're going to multiply that times 100, which should give you about 12%. I think. Do the same for the next one then. So what are we talking about now? For a heterozygote, we're looking at 47 as our one number that was given, 2 antennae is 48, and 3. So if you're looking at this set of numbers here, the smaller ones are going to be your recombinant values. So if we're looking for recombination frequencies, I'm going to take my 2 plus my 3, and that's going to be over top of 47, plus 2, plus 48, plus 3. And that would give you a recombination value of about 5%. Okay, so that's it as far as doing those math problems. And this is the only one like that that you have to worry about. I just wanted to go through it because we hadn't really had any big examples for that. All right, guys, the rest of those you'll turn in. You can either take a picture of it and submit it to me, or if you're in class, you can just hand me that piece of paper. But again, it took me about 5 sheets of paper, 4 to 5, to get all these on there. Space it out, take your time, and I'll see you later.